So this lecture, we're going to introduce the idea of hidden Markov models. So this is kind of a new topic, moving away from multiple testing now. So hidden Markov models you can think of as kind of combining ideas from mixture models and Markov chains. Okay, so one way of thinking about it is it's a mixture models where the mixture the latent variables that indicate which component you came from form a Markov chain. So as an example, a kind of a motivation, think about modeling a elephant, let's say, elephant DNA again, back to the elephants, that's a hybrid between a forest elephant and a savanna elephant. So it has a parent, let's say, that's a forest elephant and another parent that's a savanna elephant. Well, okay, so that's actually not quite interesting enough to make this example work, because if you had a parent from each, you would get one chromosome that was a forest chromosome and one that was a savanna chromosome. But imagine you have a grandparent that's a savanna elephant and three others that are forest elephants. That's a slightly more complex hybrid now. So the idea is that as you look along a chromosome, the DNA that the elephant has, some of it will have come from forest and some of it will have come from a savanna origin. So it's kind of like the mixture model, except that now we've got a single individual who's a mixture, right? So we can think of the data for this single individual as the genetic data from L different markers going along a chromosome, and we're just going to model one copy of the genome. Remember, elephants have two copies of their genome. We're just going to model one copy of the genome, and we're going to say some of these X's came from forest and some of them came from savanna, and we might want to say which bits came from which, for example. So kind of like a clustering problem, but within a single individual. So we can introduce a latent, just like in the mixture case, we can introduce a latent ZL to be the population of origin for XL as L moves along the genome. So your simplest assumption would be that the ZL are independent at each position along the genome, and so that would actually just be a mixture model for XL. Then that would be, which we've already done, right? But in practice, the way that DNA is inherited is in kind of chunks from each parent. So an elephant that's actually got some ancestry from forest elephants and some ancestry from savanna elephants, the bits that are from forest will occur in chunks along the genome. They won't be independent at the different markers. So you'll get a chunk that's a savanna chunk, and then a chunk that's forest chunk, and then a chunk that's savanna chunk. You don't know exactly how long these chunks are or where they are. That's what you want to try and infer maybe from the data. So in other words, the Z's, these latent variables, are not independent. If you if at the position before you had savanna DNA, then at this position you're more likely to have savanna DNA. So the basic idea is to model that you can model Z as a Markov chain, and that's what's called a hidden Markov model. The reason it's called a hidden Markov model is that the Z's, which are latent, are hidden; they're unobserved. If you prefer to think about people than elephants, you can, so that, I don't know if you know, but most of us have some DNA in us that's from Neanderthals. So it can be of interest to try and identify for each person which bits of our genome. It's usually a small percentage, maybe around 1% plus or minus. Could be of interest to try and identify which bits of your genome were inherited from a Neanderthal ancestor. Many years ago, of course, or many generations ago. So again, the Neanderthal parts of each genome will occur in chunks. Okay. And if you're not, if you're interested in other applications other than genetics, there's lots of applications, and I've listed a few here, but example is in finance, financial applications. You can think of periods of time during time in a time series. You can think of that there may be periods of low volatility followed by periods of high volatility, and you don't necessarily know at any given point whether you're in a period of low volatility or high volatility. In fact, if you were recently in a period of high volatility, you might want to know if you started to move to low volatility or vice versa. So you could model those two hidden states as a Markov chain. If you're currently in high volatility, you're more likely to stay high volatility, but then at some point you jump to being low volatility. And of course, high-low is a bit artificial distinction. Maybe there's continuum. So we don't have to allow the just two states. We could have many states. And in fact, there are generalizations of Markov chains that allow the state space to be continuous rather than discrete. So, yeah. Okay, so let's think about the kind of remarkable thing is that these models are actually can be fit very efficiently. Okay, even if the number of states is high, in fact. But even for two states, it's not obvious in advance that you can fit them efficiently. It turns out that you can do that using ideas from dynamic programming. So that's what we're going to do. But before we do that, let's just kind of get some terminology. So there are the X's are going to be the observed data, and the L's are going to, the Z's are going to be the latent variables. And so the probability of an observed an observation given the latent variable is called an emission probability. And then the transition probabilities are the probabilities that determine how you transition between states of the Markov chain. So there are two sets of quotes parameters, maybe the emission probabilities and the transition probabilities, and one or both of these may be known or not. Right? So in the in the hybrid example, these emission probabilities is the probability of getting one or other allele given that you're from forest or savanna. So if we knew the forest and savanna allele frequencies, we know the emission probabilities. And the probability of jumping between states might also depend on, well, it actually depends on the recombination rate and how old the admixture, the hybridization is. But so maybe we could know something about these, or maybe we would want to estimate them from the data. So P may or may not be known, and we may want to estimate them. But even if we know P and we know the emission probabilities, asking, for example, this kind of thing, what's the probability that any given Z came from cluster K, that's cluster or state K? It's not obvious how to do this calculation the way it was for a mixture. For a mixture model, it was a very straightforward. You just use Bayes theorem. But the problem we have here is that the state space in Bayes theorem is very big. So it's helpful to draw a picture maybe first. So let me just draw a typical picture to get it in your mind. So the idea is that the Z's, so Z1 are the latent states. Think of these as the memberships if it, in a mixture model context. We've got this. So these are like our Z's in a mixture model, except that they now are going along some space or time, or in our example in the elephant, along the genome, and they're changing like a Markov chain. And then the idea is that we have these quote emissions. The data, the genetic data at locus 1 depends on whether you were a forest or a savanna at locus 1, and the data at locus 2 depends on whether you were a savanna or forest at locus 2, etc. So you can see it's kind of like a sparse, sorry, that should be a 3, kind of like a sparse structure here to this graph. It's a very structured graph, right? And it's this structure that allows us to do efficient computations. Okay, so let me just imagine, for simplicity, that we want to compute the probability, just want to compute the probability of the data. Let's suppose we know all the parameters. We just want to compute the probability of the data. Okay. Well, of course, that probability is the sum over all, let's call that z, or that's a vector of z's now. Sum over all z of the probability of, let's call that x, it's a vector given z, times the probability of z. Okay, and these are the emissions. And these are the Markov transition probabilities. Well, they're given by they're just the product of the transition probabilities, right? So they're determined by the transition matrix. Okay. Maybe I can write that out a bit more explicitly. You can see it's a sum over here of a product over I of P of xi given zi, and I've used probabilities as if these are discrete, but you can also use continuous. Doesn't make any difference. These, yeah. We'll need I guess this is I equals 2 to 5, and then we need a P of z1 to start it off, right? So this part is, nice and easy, but the problem here in evaluating this is that we need to sum over all possible values for that vector z. So if there are two states and it's of length n, then there are 2 to the n possible values for that vector. So there are 2 to the n terms in that sum, or if there are k states and n length n, this is k to the n terms. And that's not very good news because k to the n is big. So we can't, if k and n are, well, if n is really moderately large, then even if k is 2, this becomes impossible to evaluate. Let's say n is, we're looking across a genome, so maybe we've looked at 1,000 markers, n is 1,000, or 10,000 markers, or 500,000 markers along a genome. Okay, so if n is big, we can't just directly compute this sum. But the idea is that we can compute it efficiently in a clever way using dynamic programming. So the math we'll look at later, but just to kind of give you an idea of what the basic idea, what the basic idea is to compute, is to compute things iteratively, and to start by computing these two, that's at the start, and then to go on and compute something like, and it varies depending on exactly how you formulate it, but compute the probability of the data at the first two loci and the second z, and then to compute the probability of the net, basically add in the probability of the next two things. And you're always computing the probability of the x's up to some state n and the corresponding z. And it's by keeping track of this z, that's what, and the Markov assumption is what allows you to move to the next level and compute the next thing. So that's why you always keep, as well as computing the probability of x1 to xn, you also keep zn in there to allow you to take the next step forward. So that's the basic idea, is that you, when you get to the end here, you've got the probability of x1 up to xn and zn, and then you just have to sum over the different, whether there are k possible values for zn. So there are just k terms like that that you have to sum at the end to get that, to get this joint probability. So this algorithm we'll have a look in a bit more detail in a minute, is linear in n, right? So it's kind of remarkable. This computational complexity is linear in n, and it's quadratic in k in general. So that's the other, quadratic in k. Why is it quadratic in k? It's basically because for every step you have to compute all possible changes from one z to the other, right? So there are k possible values for zi and k possible values for zi plus 1, and you have to do a sum over all those. So it becomes quadratic in k. Okay, so let's just look at the math. This is called the forwards algorithm. So here it is here. So you just define alpha nk to be that probability I just kind of gave you a visual on. It's the probability of the data up to n and Zn equals k. So there's going to be capital K of those probabilities you have to keep track of. So alpha 1 is just the probability of x1 and z1 equals k. Yeah, so that just depends on the starting probabilities for z and the emission probabilities for x1 given z1. And then you have this recursion, which you can do basically, that computes the alpha n plus 1, the alpha's the next step given the alpha at the previous step, and the probability of going from, these are the transition probabilities and the emission probabilities at the next step. And this sum, basically, I mentioned it was order k squared, quadratic in k. There are k of these. So if there are two states, there are two of these, one for k equals 1, one for k equals 2. And computing each one, the j is summing over the possible k values. So that computing that sum is of order k, and there are k of them to compute, so that's k squared. Okay. And that forward algorithm basically just allows you to compute the probability of the data. But you may want to compute other things. For example, something you might especially want to compute is this conditional probability. What's the conditional probability that ZL came from population or state K given the data? And you can compute that by going back in the opposite direction to compute these, what's sometimes called the backwards probabilities. So when you're given the backwards probabilities and the forwards probabilities, essentially, so if you look at what these are, they're n plus 1 up to L given Zn equals k. So back to our picture, if we just draw a picture again. Sorry. I've reversed the order of the arrows here, doesn't make a difference. So, so the backwards probabilities are, well, actually, let's do the forwards probabilities again there. Say up to 3, the forwards probabilities would be the probability of all the x's up to that state there. And the backwards probabilities are the probability of, let's put an x5 in to make it clear. C5. Okay. The backwards probabilities back to that point would be this state, and these, it's like you just offset things. So by computing or maybe it's actually the probability of these given this one rather than so that you've got the forwards probabilities will allow you to compute probability of x1 up to x3 and z3, and the backwards probabilities will allow you to compute x4 and x5 given z3, I believe. Let's just check that. Yes, okay. And so when you multiply the alpha and the beta together, yeah, if you multiply these together, you get the probability of everything, x1 up to x5, given z3 equals k for each for each k, sorry, and z, and then you can use that the probability of z3 equals k given x1 up to x5 is proportional to that joint, right? Okay, so that's the basic idea. And so this forwards algorithm, the backwards algorithm, using those basic ideas, you can do all sorts of things. Once you can compute this, for example, you can essentially do an EM algorithm for the emission probabilities, the same way as we did for mixture models. Remember that basically in the EM algorithm for mixture models, the key calculation was computing what's the probability for each observation that they came from each of the different components. And so, that's the key calculation here as well. The only difference between the mixture model is that the z's are dependent now, but it still turns out that those the EM algorithm involves the expectations of the z's. So, and the z's are indicator variables basically for which component each observation came from. So if you do the math, you end up needing to compute these things to implement an EM algorithm. An EM algorithm here might be to estimate, for example, the emission probabilities. Okay. And you can do other things like the Viterbi path, which is here. So there we go. We've just talked about EM algorithms here. Sorry. The Viterbi path is to compute the most probable path given the data. So that's also something that you can do using dynamic programming, using a very, very similar idea. So once you've got your head around these, the forwards algorithm, the backwards algorithm is really very similar idea to the forwards algorithm. And then you can do the calculations and then you can get your head around all these other calculations as well. So let's have a look at this example here. So the genetic example is not so easy to visualize. So I chose here an example that's a bit easier to visualize. So it's a two-state HMM, okay, with two-state ZI is 1 and 2 still, but the emission probabilities are, instead of being genetic data, then they're normal distributions with mean K. So mean 1 or mean 2. So it's like a mixture of two normals, which we've done before, but now instead of just having data from, that's a mess, you have ordered data, and there's a Markov chain that says which observation you come from. So actually we can kind of plot the data in this way. So the red line here shows the Z, which we don't observe, which is the Z, there are 200 observations here along the x-axis. Each one either came from a normal with mean 1 or a normal with mean 2. Yeah. And so what you can see is the observations, those are the kind of the circles, right? Those are what we've got. And we're trying to infer the red line essentially from the black line. So you can also think of this as a kind of a smoothing or a change point problem. You're trying to identify the changes that occur in the mean of the X. In this case, we've assumed there are only 2 possible means. So that helps a bit. The general change point problem would allow for different means, but we could do that by allowing for more than 2 states as well. But okay, so here are the forwards probability calculations. So it's just the same math as before, and here's the code, so you can take a look at that. And the forwards probability allows us to compute the likelihood, as we've already mentioned. Just a warning here that actually I didn't implement this very carefully in terms of numerical computations. What can happen? These alphas are probabilities, right? So what you find is that they get very small. The probability of any given data set is very small, and really we probably like to work with the logs or a lot of the time. So there's a little bit of a trickiness to essentially storing the log of the sum of the alphas, and at each step just updating that. Okay. Sorry, actually keeping that as a normalization factor, and you also need the individual alpha values up to a constant. Okay, so I guess maybe the text says it better than I just said it in words. So you wonder, there are some renormalization questions that you might like to think about. But as it is, so as it happens, this being only 200 long, it's okay that we don't get the numerical into the numerics. That it's good enough to work. But if n were 2,000 or 20,000, we'd probably get into trouble, because these numbers would all get to 0 and be no use to us. Okay, so just something to think about. But if we ignore that complication for now, then this is just doing that calculation that I outlined before. And so we're computing, look, the probability for each t that it came from state 1, given all the data. The important point here is that the forwards calculations at any point t are taking the data up to time t into account, and the backwards calculations are taking the data after time t into account. And so you combine them to compute the probability of given all the data, okay, before and after time t. Because we want to know, the idea is that when we're calculating whether a particular time point came from z, let's say this one here in the middle, if we want to ask whether this one came to z, we want to take all the data into account, and particularly we want to take all the local data into account, because that's going to be the most informative. The idea is that, for this point, we might not have a good idea that it came from population 1 if we saw it on its own, but because it's in a string of points that have mean closer to 1 than closer to 2, then we might be able to guess that this one also came from the mean 1. That's it. You're using the local information to help. So let's see how you do. So the red here is the ground truth for whether you were in state 1 or 2. I think, so the indicator, this is actually the indicator for whether you're in state 2, the mean 2. And the black line is the posterior probability, this conditional probability here, of being in state 2. So you can see that the posterior probability, the black, is high, usually when the red is high, when you are actually in state 2. And it's usually low when you're not in state 2. Actually, I think it's kind of remarkable that you can, you can essentially infer this red line from those black dots. There's it looks like kind of a noisy data. It's very, even these observations here have, it's spotted that there's a jump. At least, did it get both of them? Yeah, basically got both of them. It's not 100% sure here, but you can see. Okay, so HMMs, I think they're really cool. They're also non-obvious. It's the kind of thing that unless you've seen it, you wouldn't think to maybe model data this way. But once you've seen it, you can see that there are really nice efficient computational algorithms for fitting them. And just more generally, the idea of using dynamic programming to fit models of these kinds is a very powerful idea, very widely used in many settings. So it's, this is a good place to get your head around the basic ideas. And if you want more information on fitting hidden Markov models, there's a tutorial here that's very heavily cited, a review paper about using them for, I think, in the context of speech recognition. So I recommend that.